Welcome to this tutorial on using ROS 2 with MATLAB and Simulink. Here's the learning path we'll be following throughout this tutorial. In this session, we will explore how model-based design can significantly accelerate the development of ROS 2 applications. In our last session, we discussed deploying MATLAB and Simulink ROS 2 nodes to a target device. Before addressing bugs on the target device, is it possible to identify and resolve them earlier during the prototyping phase on the desktop? The answer is yes, and the methodology I'll guide you through in this session is model-based design. To demonstrate how model-based design accelerates development and testing in ROS 2, we'll use an example of a path-following controller for a ground vehicle throughout this session. We'll explore how model-based design can enhance various stages of the development lifecycle, including desktop system design and simulation. We'll begin by designing and simulating the algorithm in a desktop environment to validate its behavior before transitioning to ROS 2. Next, ROS 2 software design and simulation. We will demonstrate how to transition the design into a ROS 2 framework, simulating the software to ensure the integration with ROS 2's architecture. Next, ROS 2 node deployment. Following this, we'll cover deploying the ROS 2 nodes onto actual hardware. Next, ROS 2 software unit testing. We will then walk through the process of unit testing the ROS 2 software, generated ROS 2 C++ code, verifying that each component functions are implemented correctly. Last but not least, ROS 2 node integration testing. We'll focus on integration testing within ROS 2, ensuring all nodes work together to achieve the desired path-following behavior. First, we'll begin with desktop system design and simulation. In this initial phase, we'll focus on designing the path-following algorithm within a desktop environment. This step allows us to model the vehicle's behavior and simulate its response to various scenarios. By addressing potential issues early on, we can save time and reduce development risks before integrating the controller with ROS 2. The model incorporates several key components: the path-following controller, the vehicle dynamics model, the camera model, and the lidar model. These components work together to create a comprehensive simulation that closely mirrors real-world conditions, ensuring the algorithm is robust and ready for deployment. In this desktop simulation, path-following controller guides the ground vehicle along a predefined path. The simulation demonstrates the vehicle's ability to follow the path, adjusting its speed and steering based on the controller's calculations. This step is crucial as it provides immediate visual feedback on the controller's performance, allowing us to fine-tune the design and ensure it meets the desired specifications before moving to the ROS 2 environment. Next, we'll transition to ROS 2 software design and simulation. In this phase, we'll transition the controller and vehicle models from our desktop simulation into the ROS 2 framework. We begin by splitting the top model into two standalone models, one for the controller and another for the remaining components, which includes the vehicle dynamics model and sensor models. Once these components are separated, we introduce ROS 2 publishers and subscribers to facilitate communication between them. This setup allows the controller to operate independently while receiving data from the vehicle dynamics and sensor models via ROS 2 messages and publishing the vehicle control commands. This is how the two ROS 2 Simulink model simulations work together. On the right-hand side, the ROS 2 simulator model is responsible for publishing images and point clouds from the camera and lidar sensors, along with the vehicle's state information. On the left-hand side, the ROS 2 controller model receives these messages, processes the data, and generates the control commands, which it then publishes. This interaction between the simulator and controller models demonstrates the publisher and subscriber communication in ROS 2. Next, we'll transition to ROS 2 node deployment and ROS 2 software unit testing. In this stage, we'll focus on deploying the ROS 2 nodes onto the target hardware and then proceed with unit testing. This ensures that the nodes not only deploy correctly, but also function as expected when isolated. For the ROS2 software design node, we can generate ROS2 C++ code, build the model to create a standalone executable, and then run it on either the local host or a remote device. This process allows us to transition the design from simulation to a deployable application, ensuring that the software can be executed independently on the target platform, whether locally or on a remote system. In this example, we simply click the Build and Run button in the ROS2 software design node. Simulink generates the C++ code, compiles it, and immediately runs the executable. Once the ROS2 node is up and running, it begins transmitting data to the ROS2 simulator node, demonstrating the communication and integration in the ROS2 framework. Furthermore, we can monitor and tune the deployed ROS2 node directly from Simulink using external mode, which allows us to debug the design in real time. The external mode provides a powerful tool for observing the node's behavior during runtime and making adjustments on the fly, ensuring optimal performance and quick resolution of any issues that arise. In this example, when we click the Monitor and Tune button, Simulink generates the ROS2 C++ code, builds it, and immediately runs the node. Similar to the previous example, the ROS2 node begins transmitting data to the ROS2 simulator node. However, the key difference here is that we can monitor signals directly from Simulink and tune parameters in runtime. For instance, we have two scopes set up to monitor the vehicle commands and vehicle states. Additionally, we've added a dashboard that allows us to modify the operating mode, providing direct input to the controller. This setup offers greater flexibility for debugging during the development and testing phase. Next, we'll move on to ROS2 node integration testing. In this phase, we'll focus on verifying that all the ROS2 nodes work together as intended. Integration testing ensures that the individual components, such as the controller, sensors, and vehicle dynamics, not only function correctly on their own, but also interact properly within the larger system. In this example, in addition to the previous two ROS2 nodes, we've added a ROS2 service client in MATLAB. This service client is used to request a change in the operating mode of the controller. By adding this functionality, we enhance the system's flexibility, allowing the controller to dynamically adapt to different conditions or requirements. This also demonstrates how additional ROS2 services can be seamlessly integrated into the existing framework to extend the system's capabilities. Let's examine how these three ROS2 nodes work together. As introduced, we've created a ROS2 service client that allows us to send service requests to the ROS2 software design node. By altering the value of the service request message and sending it, we can observe how the controller's operating mode responds accordingly. This interaction highlights the dynamic communication between nodes and the controller's ability to adapt based on the received service requests. We have now walked through the entire process of using model-based design and the V model with ROS2 at a high level. Next, let's discuss why use model-based design, why it is important. In traditional development workflows, a gap often exists between the initial concept and the final product. This gap can arise from incomplete specifications, misinterpretation of requirements, and errors in design and implementation. These challenges lead to costly iterations and delays, especially when issues are discovered late in the development cycle. Model-based design addresses these challenges by shifting the focus to a model-centric approach, enabling teams to bridge the gap between concept and result effectively. Model-based design enables performing early validation and verification. By creating executable models of the system early in the design phase, teams can validate functional requirements and verify system behavior before hardware or physical prototypes are built. This reduces the risk of costly rework later in the process. Moreover, simulations with models enables teams to quickly test multiple design ideas and iterate to optimize performance without waiting for physical prototypes. Here is some evidence highlighting the differences between model-based design and the traditional development process. By following the V model, we've demonstrated how model-based design allows for continuous validation and verification at each stage of development. This approach contrasts with the traditional process, where testing often occurs late in the development cycle, making it more challenging to catch and fix issues. Through this walkthrough, you can see how model-based design, by shifting left, shifting earlier, provides a more integrated, efficient, and reliable development pathway. With traceability from requirements to the final product, model-based design facilitates iterative development and easier updates, especially for complex systems requiring long-term evolution. To shift left within the V model, we can perform several activities to ensure the quality and safety of the ROS2 software design. In this session, we will go through the key steps together, including checking compliance with industrial standards, managing requirements, automating tests, and analyzing coverage. These activities allow us to identify and address potential issues earlier in the development process, enhancing both the reliability and safety of the final software. Simulink offers industry-recognized checks and metrics to identify violations of modeling standards and guidelines as you design. It supports various high-integrity software development standards, including MISRA-C for C language in critical systems, DO 178C for aerospace, ISO 26262 for automotive, ISO 25119 for heavy machinery, EN 50128, or railway systems, EN 62304 for medical devices, IEC 61508 for electrical and electronic systems. These standards help ensure that your software designs meet rigorous safety and quality requirements for high-integrity systems across different industries. Here's an example that demonstrates how to perform checks in Simulink. Simulink provides tools like the Model Advisor to help you identify potential issues and ensure compliance with industry standards. By running automated checks, you can validate your model early in the design process and address problems before they become costly. The Model Advisor can be used to evaluate your model against MISRA-C guidelines, a widely adopted standard for safety-critical software development. For example, a warning is issued for equality and inequality operations on floating point values within the pure pursuit block. This warning indicates potential precision or comparison issues, which could affect the accuracy and reliability of the controller. We can also run checks for the IEC 61508 subsets, a standard for functional safety. For example, a warning is issued if there is inconsistent vector indexing, where some Simulink blocks use zero-based indexing while others use one-based indexing. This inconsistency could lead to errors during execution, violating IEC 61508 safety requirements. In summary, the results from these checks help identifying compliance issues, such as numerical precision, indexing, or other implementation challenges. It provides actionable insights to improve the model. Last but not least, it ensures alignment with critical safety and coding standards. Next, we'll move on to managing requirements. In this phase, we'll focus on how to systematically capture, trace, and manage the requirements throughout the development process. This ensures that all project needs are met and aligns the design with stakeholder expectations. You might be familiar with these types of requirements. System architecture requirements. These can be created directly in Simulink to define the overall structure and design of the system. Interface control requirements, such as ROS to publisher and subscriber specifications, ensuring proper communication between components. Performance requirements. For the pure pursuit controller, ensure that it meets the desired speed and accuracy. Logical requirements. For supervisory logic control, defining the decision-making processes within the system. And you might have heard about safety requirements, cybersecurity requirements, functional requirements, diagnostic requirements, user interface requirements, and regulatory compliance requirements. Managing requirements helps identify gaps in both implementation and testing. By systematically tracking and analyzing requirements, we can ensure that all aspects of the project are covered, highlighting any areas where implementation may be incomplete or where additional testing is needed to meet the project's objectives. Here's an example showcase how we can manage requirements in Simulink. From the Apps tab, we open the Requirements Manager. In this example, we've already created 3 requirements, each with an implementation and verification status. By dragging a requirement onto a Simulink block, we assign that requirement to the implementation, and you'll notice the implementation status updates automatically. We can also open the Requirements Editor to review the detailed specifications of each requirement. Additionally, we can generate a traceability matrix, which is often required to comply with industry standards. Next, we'll move on to automating tests and analyzing coverage. In this phase, we'll focus on how to automate the testing process and analyze test coverage to ensure that all aspects of the system are thoroughly verified. This step is crucial for confirming that the design meets all requirements and avoid having unintended functionalities. In this demonstration, we'll cover several key aspects. Scenario-based testing, evaluating how the system performs under different simulated scenarios. Requirement-based testing, ensuring that all requirements are met through targeted test cases. Test report generation, documenting the results of our tests for review and compliance. Coverage analysis, analyzing how thoroughly the tests have exercised the model to identify any untested areas. You might be familiar with unit testing, model in the loop, MIL testing, software in the loop, SIL testing, hardware in the loop, HIL testing, and back-to-back testing. All of these testing methodologies can be automated within Simulink, streamlining the verification process and ensuring consistency across different stages of development. This automation capability helps to efficiently verify the functionality and performance of the system under various conditions. All of these activities are essential to ensuring the software's quality, safety, and compliance. By systematically performing these tests and analyses, we can confidently validate that the software meets industry standards, operates safely, and adheres to all required regulations. Here's a demonstration of how we can perform these tasks in Simulink. Starting from the Tests app, we open the Simulink Test Manager. We've already created several test cases for desktop simulation, requirement-based testing, and scenario-based testing. Let's take the requirement-based testing as an example. We can link the requirements directly to the test case, enable coverage collection, and then run the test. Once the test case is completed, we can review the test results. For example, we can examine the simulation output through graphical figures. Additionally, we can generate a test results report, which can be customized to fit our specific needs. Here's an example of how the report looks. From the coverage results, we can see that this particular test case didn't achieve 100% coverage in decision points. By clicking the link, we can dive into the details. Simulink will highlight the coverage results, marking blocks that are not fully covered in red. The coverage report on the right-hand side provides all the detailed information, helping us identify areas that need further testing or refinement. Last but not least, we can explore status and quality of testing activities using Model Testing Dashboard. In summary, this example demonstrates how model-based design accelerate in developing and testing a path-following algorithm for a ground vehicle using ROS 2. I hope this has provided you with a deeper understanding and valuable insights into the benefits of using model-based design, and that you've found inspiration for applying these techniques in your own projects. Thank you for participating in this session. Let's recap what we have covered in this tutorial. We began with an overview of ROS 2, outlined the key differences between ROS 1 and ROS 2. Next, we went over the installation process for ROS 2 in MATLAB. Next, we discussed the core concepts of ROS 2, including ROS 2 nodes, domain ID, topics, messages, quality of service, QoS, services, action, and parameters. Moreover, we covered logging and visualizing ROS 2 data. Additionally, we discussed accessing ROS 2 time and synchronizing ROS 2 nodes. Next, we explored generating C++ code and deploying ROS 2 nodes from MATLAB and Simulink. Finally, we discussed how model-based design accelerate developing ROS 2 applications. I hope this tutorial equips you with the foundational knowledge and tools to effectively work with ROS 2 in MATLAB and Simulink. Thank you for your attention.